A very good morning. We are at the Ying lab in Madison, and we are now with Holden Rogers, who is doing his PhD here, and he is in research with PLN, and we are in his lab. And Holden, can you tell us about more what we see here?
Yeah, so this is our instrument room where we have two mass spectrometers that we use to do top-down proteomics. So in the G lab, we focused on studying intact proteins in relation to cardiovascular disease. So we look strictly at how PTMs play a role in disease, and in particular, um, with phospholamidin, it's been really good because it's a combinatorially modified protein. It has two phosphorylations and an internal acetylation, as well as a palmitylation. And so with top-down proteomics, we're not only able to see all these post-translational modifications, but in particular, we're able to look at the mutation as well. So with the arginine 14 deletion, since it's heterozygous, we're able to see how the mutation impacts these modifications on phospholamidin, as well as other cardiac biomarkers like cardiac troponin I or myosin light chain isoforms. And so in this room, we have our instruments, and we're able to study phospholamidin directly from human cardiac tissue, as well as human-induced pluripotent stem cells. And we're able to see how this disease impacts the modifications on phospholamidin in different patients. And so we're able to get a real individualistic approach to studying this disease.
Thank you very much, Holden.
Yeah, no problem.
Impressive story, and we are really enthusiastic about the technology we have, because one of our biggest questions is, why does half of our people develop the disease and the other half is safe? And with your technology, we can get one or two or maybe even more parts of that puzzle complete.
Exactly. So the goal is to look at patients that are symptomatic or asymptomatic, use human-induced pluripotent stem cells, and see if we can tease out any post-translational modifications that are different between the two, which may lead to different mechanisms and the pathogenesis of the disease. And so we're really hopeful that our technology is able to bring a new piece to the puzzle in analyzing how different patients progress with the disease, as well as just getting a better understanding of how the disease manifests in human patients. And so we're hopeful that this can lead to hopefully new therapeutics, or a better understanding at least of how this disease works and manifests, and work our way towards a cure.
Thank you very much.
Yeah, no, thank you.
A very good afternoon, Ying. I'm at your lab in Madison, and you have a beautiful technology which can help us, because one of our big questions is, what does half of the carriers make them ill, and what saves the other half? But you have an intriguing technology of helping us with a little piece of that puzzle. Can you tell us a little bit more about that?
So we have this technology called top-down proteomics, which study intact proteins and analyze the proteoforms. So we try to say this is a technology that can connect the genotype with clinical phenotype. As you know, when genotype doesn't necessarily connect to the phenotype. Patient with same mutation could have completely different clinical outcome. And some people has exactly same mutation. They can develop a very severe disease outcome, versus other patients, they live happily without any symptom. So there is obviously a gap between the genetic mutation and what's the clinical outcome. So it is now well known the genotype is not good for prognosis, like predicting the prognosis. So what's really in bridge in between, as we call proteins, and proteins, because they are the real effectors of life. And as you know, many drugs are targeting the proteins, right? This is why we need to check the proteins. So if you say you have the mutation, you have this, the PLN mutation, and then we check what's their protein level differences, whether their phosphorylation, post-translation modification changes or not. As you know, this phosphorylation is critical for function, right? Yeah. So if the patients still have these phosphorylation, maybe they're okay, or I mean, if this phosphorylation level changes, this may be more connected with, the disease outcome. So we actually recently published a paper in PNAS, which is another disease called HCM, which is also inherited disease. We find that the proteoform, the protein, these post-translational modification changes is actually independent of genetic mutations, but they're very closely associated with clinical outcome. So as in a short summary is the protein forms, okay, we call proteoform right now, that are being obtained by this top-down technology will give us much closer information to the clinical phenotype. Yeah. For example, you have the same mutation but different protein form, proteoform. Like my student Holden did this beautiful work that he can see each how the mutations, what are their presentation in these PLN proteins, and how the other proteins interacted with this PLN, how they change. Yeah. And then we hope is have more of a samples from these disease carriers. So then we have much stronger, do power analysis statistically. Yeah. So we can see, okay, this proteoform changes will link directly to the final clinical phenotype. So in this case, we think about, we can use this to do kind of a proteoform like atlas. So it was called like personalized genomics as reality. You can get your personal genome sequenced for a small amount of money, right? Like 23andMe. But the proteoform type is not ready for doing the personalized, like proteoform, like individualized proteomics. So we are trying to make this available. So in the future, that's our vision of the future for patients, especially for genetic disease. Patients have this genetic mutation. You want to know what are your chances of getting disease. So we are trying to do analysis at the protein level. Then we want to see what this mutation, whether you are in the good category or whether in the bad category. So that case, we can do better prognosis. But I should say these are the future visions. Right now, we need more samples to making sure there is this bridge. So we call this proteoform is a bridge between the genotype and the phenotype, that we can get those precise information to inform the care team. I met with cardiologists because they really have difficulty with inherited disease because they don't know how to treat the patient. If they treat the patient too early and the patient is not going to develop disease, I mean, this is not good, right? But especially like a PLN, this is deadly disease. So if you wait too long until the symptom comes, then you don't have a cure. The heart transplant is the only route. And there's only very few heart transplant available. Peter, you are a lucky one, but not everybody is lucky.
Extremely lucky.
But not everybody, many people probably cannot wait for the heart transplant. So this is why we say these are the future technologies. We're going to have this, make it a personalized proteoform atlas available to patient in the future.
And now Roger is talking to Groningen, the UMC Groningen, to get more material from the Netherlands shipped into Madison on which you can do further research.
Exactly, yeah, we're kind of taking a twofold approach. One, looking at the end-stage heart tissue from UMCG, taking the patients that have had the heart transplant and taking their former heart and doing analyses on them and seeing, as Ying said, how these post-translational modifications change between healthy and disease state. And then we take another approach using human-induced pluripotent stem cell-derived cardiomyocytes, where we can take cell lines derived from symptomatic or asymptomatic patients and compare and see, okay, are these post-translational modifications different in symptomatic patients versus asymptomatic patients? And that can just help us overall with disease pathogenesis as well as just understanding the mechanisms behind the disease. And so we're really happy to work with you guys and use our top-down proteomics technology to get a better understanding of the PLN-R14 deletion disease.
Yeah, which is great, and we're really enthusiastic about it. And for the cell material that will be made available by Stanford, which we cooperate also very closely.
Exactly, yeah, we're working with Ionis.
Ionis Karakikas, and he is also a great researcher on the project. And we will do everything we can to make material available to you to explore what you explain as how does the genotype translate to the phenotype.
Exactly.
Yeah.
And really, we are very passionate to contribute to the to the PLN Foundation. We really want to make this technology available to save people's life. So we always said this is called the bench to bedside translation. I think this is a perfect project to demonstrate it, and we care about all patients. So as I said, we want to make this technology available to you. And so, I mean, a lot of time we were just sad that we have powerful technology, but it is not being translated into the clinic. And thank you, Peter, for coming to visit us and tell us all the stories about yourself and about the PLN Foundation. So we really, as I said, we really have a feel for the patient, and we hopefully we will contribute to their kind of a health and bring a future, as I said, technology innovated platform.
Yeah, that's all the carriers which are waiting for everybody's help, and you're really passionate scientists working on it. So I wish you all the luck and everything you need, and we are there to help you.
Awesome, thank you, Peter, so much.
Yes.
Okay, thank you very much
absolutely.
For this interview.
Thank you for visiting us, and we are so happy that our research could really help save people's life.
We go for it.
Yes.
A very good afternoon. At this moment I'm in Scripps University, close to San Diego in California. And I'm here with a very enthusiastic team of people, and we have been just discussing a new project using computer technology to try and find treatments for our disease. Stefano, Professor Dr. Stefano Forley, but I hope I can say Stefano. Can you tell us a little bit about it and everybody else on his role in this project?
Yes, I'm Stefano Forley, and I'm the associate professor here at Scripps in La Jolla, California. And our lab is specialized in development and application of computational methods for drug discovery, especially early drug discovery. And so I'm lucky to have a brilliant team of young researchers that help us developing new methods and hopefully finding new potential drug candidates that can be used for the development of cures for molecules.
I'm Matt Holcomb. I'm a staff scientist in the lab. I got my PhD from Scripps Research a couple of years ago now, and I have a background in chemistry, and I've been trying to improve the modeling methods that we use so we can be more accurate in our predictions, and I try to keep his ideas on the ground and practical.
I'm Shenghao Luo, and I'm a PhD student here, and I guess I will just do whatever I kind of help to facilitate this project moving forward.
I'm Manuel Llanos. I'm from Argentina, and I'm a postdoc here at the Forley Lab, and I work also in simulations and drug discovery using computational techniques.
Yeah, we'll bring you guys in contact with Stanford to cooperate with Stanford, and let's make it a very interesting cooperation, and which gives new perspectives for our patients.
Looking forward to it, yes.
Thank you very much, and keep up the good work.
Thank you.
Thank you.
At this moment, I'm in the Stanford University in the United States, California, and I'm here together with Rachel. And Rachel is, because how many years are you already on the PLN research?
I'll be starting my third year working on PLN and studying PLN.
So you're doing a lot of work in PLN.
Yes, a lot of work.
it's a small, very small protein, but it keeps lots of researchers all over the world busy.
Exactly, exactly. It's a small protein, but it's so important to how the heart functions, so it's really important to study it and understand better.
Yeah, and you're in the heart muscle cell looking what is happening to it and how, because we know there is a mutation, and what makes it behave differently. Can you elaborate a little bit on that?
Sure. So what I'm really studying is, as you said, we have the mutation, and we know that it's making something different happen with the protein, but there's still a lot that we don't know about why this protein behaves differently. So I'm looking at how the PLN, both our regular PLN and the one with the mutation, how they get transported through the cell, and when they're transported, how do they do their job? Because I think maybe that can explain why the mutated form maybe isn't doing its job properly.
So in period of time, because your project is ongoing, you can tell us where it goes and whether the mutated one goes somewhere else or to the same place,
Exactly.
or whether it behaves differently.
Exactly. So by understanding how the regular, I shouldn't say regular, understanding how the wild type form of PLN functions, from there, once I have that established, then I can figure out why the R14 del PLN is functioning differently.
Yeah, because our $1 million question, to call it that way, is, you know, roughly half of the people who carry the mutation do get the disease. What saves half of them? And
Right.
what brings the trouble to the other half? This might be an interesting piece of that puzzle again.
Exactly, because understanding these pathways, it can be a clue as to what that difference is.
Yeah. Well, wishing you lots of success. I think we will see each other in September in Crete.
Yes, yeah, I'm very excited.
And I'm also excited to see your results then.
Yeah, thank you so much. Thank you.
Well, we'll keep you updated, and I will talk to Rachel in Greece again, and then I hope she has more information for us.
Definitely. Thank you.
Een hele goede dag allemaal. Vandaag de laatste dag van een rondreis door de Verenigde Staten, waar ik heel veel onderzoekscentra die aan PLN werken heb mogen bezoeken. En ook een heel aantal farmaceuten die meewerken om tot een oplossing te komen. De afgelopen 2 dagen ben ik hier op Stanford geweest, bij het lab van Ioannis Karakikis en bij Mark Mercola. Ja, maar bij alle onderzoeksinstituten weer prachtige dingen gezien. Gisteren ook weer een prachtige dag gehad met hele mooie discussies. Wauw, we komen echt verder, mensen. Het tempo zit er fantastisch in en we komen er. Maar wat ik nog even mee wil geven, dit is ook wel een fantastische omgeving, die Stanford University. Ik sta hier echt op zo'n prachtig punt. Ik laat jullie achter me even zo meekijken. Het is echt een omgeving waarin je het gevoel krijgt, ja, ik wil leren. Ik leg het me uit. Een prachtig universiteit. Dus er komt meer nieuws.